Okay, question 1.3 from, well, let me show you the book. From this book, Generalized Linear Models with Examples in R. Okay, so question 1.3 starts out being very similar to questions 1.1 and 1.2, in which we look at the fit of the systematic component of a model with data, and then we're asked to decide which is the best or better. And so at this point, I think that we kind of understand this process. Very basically, just like questions 1 and 2, probably the cubic or quartic model are doing the best compared to the quadratic model. And we can tell because of, well, how close the line is to the data points. And it just seems like there's more distance between the line and the data points in the quadratic compared to the cubic and quartic. Having said that, the cubic model looks to be just about as good as the quartic, if not, well, it's very close to being just as good. Well, since the cubic model is simpler, right, it's only going to have terms up to x cubed, whereas the quartic model will have terms up to x to the 4th power. The simpler model we tend to prefer, all else being equal. Okay. So that's all fine and good. But now this question 1.3 asks us something a little bit nuanced. It says, okay, these data points here, these were actually generated by a computer randomly using this equation right here. And there's nothing special about that equation, okay? And there was some randomness associated with that. But in other words, this was the this is like the regression that was actually used to generate the data, right? So normally we're using regression to figure out how to make this line, right? But here we could go the other way, and we could say here's the line corresponding to the model. Now generate data from it. Okay, we could go both ways, and that's what that's doing. It says, which is not a polynomial at all. Explain what this demonstrates about fitting systematic components. Okay, so let's address that. So what we're meant to notice here is that the data generating process, that this right here, is not equal to the model that we're using to model that data. Okay, and so what are we to make of that? And so maybe the first question is, okay, well, is this a problem? And the answer is, well, no, not really. And the reason is because models are never correct, okay? In fact, a lot of statistics relies on these linear models that have a form kind of like this because of their ability, not because we think that all processes are actually corresponding to this type of a thing, but because these types of models tend to fit the data. Okay, again, it's not because we believe that the data generating processes are actually this. Okay, it's because this type of model tends to be able to fit. Well, we can use it and understand how this type of model fits data. Okay, so the overall point here is that models are probably never correct in the sense that there isn't in nature a term that exactly corresponds to beta 1x or something like that, okay? That's just an approximation of some features of the data generating process, okay? And but even if a model were perfect, right, we're almost never in a position where we can know that that's the case. I call this an epistemological position, right? So this is a little bit of a cheating example because the authors kind of pull back the veil and say, this is the data generating process, okay? But generally, we don't know the data generating process at all, okay? We're using tools like regression to understand the system, but that does not mean that our regression is really mapping on with complete fidelity to the data generating process. So what does the fact that our data generating process is not completely analogous to our regression, or said differently, what does it mean that we can use an expression for our regression that is not completely identical to the actual data generating process, what does that say about regression or about modeling together? Well, it's that our models are they're always approximations, and the expression or the derivation of those approximations need not completely correspond to the form of the data generating process, and that's okay. Ultimately, a model is its worth is determined by its accuracy in representing not the data generating process, but the data of the data generating process. Okay. Now, that's not to say that there aren't occasions where we are actually trying to generate models that do somehow correspond to what would be a mathematical representation of the data generating process itself. Okay. So, for instance, when we're worried about causal modeling, we're kind of trying to do something very similar to that. But even in that scenario, the thing that we're using to test whether or not our model is analogous to the data generating process, or identical to, or close to, or something like that, is again the accuracy of the predictions of the model with the data that the data generating process generates. Okay, that was a mouthful. Okay, that's it for this one.